Good day everyone, thank you for joining me today. In this presentation, I will be walking you through a practical case study on labor, allocation and cost optimization using linear programming and the graphical method. We will see how a simple yet powerful operation research technique can help companies make smarter, most cost-effective decisions when hiring and allocating workers. Let's dive in. This case is based on a very common real-world challenge that many project-based companies face: how to allocate limited labor resources while keeping overall costs as low as possible. The company in our scenario need to hire two types of workers: skilled workers, who are paid higher wages because of their expertise, and semi-skilled workers who earn less but still play critical roles. Like most organizations, this company operates under tight constraint, limited budget, specific skill mix requirement, and restriction on total headcount. Situations like this are everywhere: construction projects, manufacturing plants, event management, IT services. Anywhere you have to balance cost, capability, and manpower limits. By the end of this case, you will see exactly how linear programming turns these messy real-life restrictions into a clear, optimal hiring plan.
The company aims to have enough workers to meet project requirements and minimize the total labor cost. However, they must follow these conditions, which are that the number of semi-skilled workers must be twice the number of skilled workers. It means y equal to 2x. The total number of workers must be between 30 and 60. That means x plus y must between the number of 30 and 60. And of course, the last one is the number of workers cannot be negative. This forms a resource allocation and cost minimization problem suitable for linear programming. For part of the key insight, constraints shape optimal choice. Linear programming can help to find the optimal solution within limited feasible choice.
For this part, in a labor allocation problem involving skilled and semi-skilled workers, linear programming helps determine the most cost-efficient hiring plan. First, the decision variables are defined to represent the number of skilled and semi-skilled workers required. Next, a cost minimization objective function is formulated by multiplying each worker type with its respective wage rate. After that, the constraints are established to reflect project requirements such as minimum labor hours, skill needs, productivity conditions, and availability limits. These constraints are then graphed to form the feasible region, which shows all valid combinations of both worker types. Finally, the objective function is evaluated at the corner points of this region to identify the combinations of skilled and semi-skilled workers that results in the minimum total labor cost.
Now I would like to explain fully related to solutions of case study, as we know that this case study is about the minimization cost of by having two categories of workers, which were skilled workers and also semi-skilled workers. So we will solve these solutions of this case study one by one. So for first, let X is number of skilled worker and Y is the number of semi-skilled worker as the questions given. While for that one, we will formulate the objective functions for minimization of the labor cost. That is, Z is equal to 80x plus 30y. So for these objective functions, they also need to fulfill all the constraints given for the questions and the case study given. That is, 2s is equal to y, 30 smaller equal to s plus y, and also smaller equal to 60, which s, y are not negative d, which means workers cannot be negative values. So to find the optimal solutions for this linear programming approach, we will arrange the constraint in terms of equation y is equal to ms plus c, or the general solutions that are as plus by is equal to c. So let's consider that 2s is equal to y is 1. So from 1, we can change the side, so y is equal to 2s. So we consider this equation is 3. From 2, 30 smaller equal to s plus y and also smaller equal to 60 have two constraints actually. So by separating the inequalities, we can know that 30 is smaller equal to s plus y, which we can define this equation as 4. From 4, we can exchange the sides, both sides. It can become x plus y more than equal to 30. We can consider this equation is 5. Now, let's take a look about the next constraint, which is last constraint. So, as usual, remain the positions x plus y smaller equal to 60. Therefore, the three constraint was already exist to find the optimal solution, which was y is equal to 2s, x plus y more than equals to 30, or and also x plus y smaller equal to 60, which x and y cannot be negatively. They are more than 0. The workers cannot be negative after arranging the constraints. So for this part, I would like to talk about to find the coordinates to sketch a graph. Okay, so for the graphical solutions, so let's say y is equal to 2s, where s is equal to 10, y is equal to 20. Where s is equal to 20, substitute the equation of s equal to 20 into this equation, so y is equal to 40. While for s plus y is equal to 30, when s is equal to 0, y is definitely is 30. When y is equal to 0, s is equal to 30 for this constraint of this linear equation. While lastly, for the last constraint, s plus y is equal to 60, when s is equal to 0, definitely the coordinate of y must be 60. When y is equal to 0, s is equal to 60. So now let's take a look about the graph by using the Microsoft Excel to build this graph. So as you can see that they got two optimal solutions of the corner of the coordinates, which was 10 and 20 and 20 and 40. These both coordinates is the optimal solutions of minimization cost that are fulfilling these three types of constraint, which means y is equal to 2s. Exactly, the optimal solution must only regarding to the y is equal to 2s, the coordinate of the point, by fulfilling the constraint s plus y is equal to 30 or s plus y is equal to 60. Alright, so we already got these two coordinates of corner, which is optimal solutions. So we will substitute these two coordinates, which was 10 and 20 and also 20 and 40, substitute the values into the objective function, which was z is equal to 80 s plus 31. So by substituting 10 and 20 into the objective function z, we can find the cost is Rm 1,400 ringgit. While substituting 20 and 40 into the objective function z, you find the value of the cost is 2,800. So we can compare to these two questions. This case study of the minimization cost is 1,040, which means they need to require 10 of skilled workers and also 20 skilled workers that are do it for this project, to conduct this project by fulfilling all the constraints by having the minimum cost, which was 1,400. That's it.
To maintain efficiency and cost effectiveness, the company should strictly adhere to the required 2-to-1 ratio of semi-skilled to skilled workers as a foundational rule for its current hiring strategy. Furthermore, to secure long-term advantages, the company should consider investing in automation to reduce its reliance on higher cost skilled labor and provide training programs to expand the capabilities of its semi-skilled workforce, hence increasing their capability. It is also advisable to periodically re-evaluate whether the ratio constraint itself remains necessary as project demands evolve. Finally, the company should rerun the linear programming model whenever the project requirements change to ensure the labor allocation strategy remains optimal. Collectively, these recommendations will help optimize labor deployment and reduce costs over the long term.
Reflection and attention. This case can be attended in various ways such as first, changing the radio For example, to 3-1 will completely change the optimum point. Second, adding overtime, scheduling or maximum limit will turn this into a workforce optimization model that are similar to what real companies were using. Third, adding more worker criteria will turn this into a multi-variable situation and case. Is criteria for worker more than 2 types of worker, even the graphical method is simple and rigid, but only work for 2 variables. The most common problem require computer to serve as a self-solve or simple method to solve. In conclusion, this case study demonstrates how a real-life labor planning problem can be transformed into a linear programming model. Through the graphical method, we identify the feasible region, evaluate potential solution, and determine the lower cost labor allocation. Optimal solution of hiring 10 skilled and 20 semi-skilled workers gives the minimum cost of our M 1,400 for doing a project. It shows the power of LP in helping organizations make structured, data-driven, and cost-efficient decisions.
And thanks for your attentions to listen for our presentations. Thank you so much. Okay, so good night, guys. Okay, so I would like to explain about the guidelines and also the tips for we will relate to one case study, one question, which is just this case study questions. Okay, so this guys can understand the concept or not once I edit done my video. Okay, you guys can have any questions or not so far? I'm your mic. Okay, one more. Okay, good. Okay, I think that's it. Okay, we can dismiss this meeting. Okay.